Now let us go into some detail about the Newton's law of cooling. So the Newton's law of cooling states that the heat transfer is proportional to the surface area of the object and the temperature difference. The proportionality constant is defined as the heat transfer coefficient. An example here is a solid surface over which fan is moving, as well as in natural convection. This is the particular ceiling, there is free convection because of radiator, and this is the particular explanation. This is a T body, this is the heat, this is the body at temperature T, which is T body temperature, and there is heat transfer from the body towards the ambient fluid that is moving, which is at T infinity. So the Newton's law of cooling states that Q is nothing but a related to area of the body and the temperature gradient between the body and the surrounding fluid, and the proportionality constant is heat transfer coefficient, that is Q is equal to HA delta T. This is the Newton's law of cooling. Now let us discuss the third mode of heat transfer, which is radiation. Now heat transfer as radiation emitted energy. Now heat transfer due to radiation is nothing but the energy emitted in the form of electromagnetic waves, which is thermal energy emitted in the form of electromagnetic waves. This does not require any medium, so it can happen in vacuum also. Thermal radiation forms a part of electromagnetic spectrum, which ranges from radio waves to gamma rays. So it is part of a electromagnetic spectrum of the particular range, and rules that apply to any type of radiation also apply to thermal radiation. So there are other types of radiation also, like light radiation and gamma rays, X-rays, etc. Electromagnetic waves emission carries heat energy in this particular mode of heat transfer, and heat energy intensity is here is function of body temperature and surface characteristic. We will discuss this in detail, where the heat intensity is given by the product of sigma and temperature raised to 4, and radiation is effect is important only at high temperatures. We usually neglect thermal radiation effects at low temperatures. Now going into radiation, let us discuss what do we mean by black body. A black body is an ideal radiator, which is referred to as idealized concept of a radiator. It absorbs all the energy that reaches it, all the thermal energy, and it reflects no energy that reaches it. What it means is the energy radiated or emitted by a black body is maximum, and it is given by Stefan Boltzmann's law, that is Q, that is energy emitted, is nothing but sigma into T raised to 4, where sigma is the Stefan Boltzmann constant, whose value is 5.66 into 10 e to the power minus 8, and this is the particular Stefan Boltzmann constant, and this is temperature T. This is the energy emitted by a body at temperature T. An example here is, let's say we have a particular thickness body, and Q is the incident radiation on this particular surface. Now some of the energy, that is RQ, is reflected radiation energy from this particular surface. Some energy is absorbed by the surface, which is alpha Q, and some energy is transmitted through the surface and it moves ahead of the surface, that is it passes through the surface, which is referred to as transmitted radiation energy, that is tau Q. So these are quantified by absorptance, reflectance and transmittance are the properties which we will discuss when we discuss the radiation lecture in detail. But what it means by sum of all this should be balanced, which means the reflectance, absorptance and transmittance should be equal to 1, the sum of these three properties. Now this was about basically black body or idealized radiators. Now let us see what happens in real condition, that is real bodies emit less energy than a black body. So the Stefan Boltzmann's law is not applicable as it is modified, and we say that there is some amount of fraction that is multiplied to the radiation energy emitted by a black body. So in case of real bodies, we have Q is the product of epsilon into sigma into T raised to 4, where E or epsilon is the emissivity, which is the number between 0 and 1. So this, if we multiply this by the radiation emitted by black body, we get the radiation emitted by real body. So we refer to real bodies as something called as gray body, which is in which the emissivity is the average over spectrum, that is it is independent of the frequency over of the spectrum, and in that case both the body and its surrounding emit thermal radiation. In the real scenario, both the body and its surrounding will emit thermal radiation, and the net heat transfer will be from the hotter to the colder body. So if we consider a case where we have a particular real body at temperature TW, and the surrounding is at temperature T infinity, we will have the surrounding is also emitting radiation, that is Q infinity, and the body is also radiating emission, which is QW. So the net is basically Q net, which is epsilon A into sigma into the temperature gradient to the power 4. So this is the Q net or heat transfer between these two bodies by radiation. Now, since we have covered concepts of conduction, convection and radiation, now let us move ahead and discuss some of the non-dimensional or dimensionless numbers which are important from analyzing heat transfer. First is Nusselt's number. So this is the ratio between total heat transfer in convection dominated system to conductive heat transfer, and it is given by HL by K. That is Nusselt's number. So it is the ratio of total heat transfer to the conductive heat transfer. There is another dimensionless number which is important, known as Grashof number, which is the ratio between buoyancy force to viscous force, which is given by this particular ratio, and it involves density, it involves gravitational force, temperature gradient, characteristic length, as well as viscosity in the denominator. We also have Prandtl number, which is ratio of momentum diffusivity and thermal diffusivity, which is given by this particular ratio. Here we have Cp mu by K, which is Prandtl number, and the Prandtl number is about 0.01 for liquid metals, about 0.7 for most gases, and about high, that is 6 for water at room temperature. These are just some of the values that are commonly encountered.